So in the last class, part 2 of Bertrand's postulate, we have proved this result, that is, the product of prime is less than or equal to x is less than or equal to 4 raised to x minus 1, right, for all real numbers x greater than or equal to. Now we are going to estimate one more quantity. So before that, we need a prerequisite, which is a theorem by Legendre. What do you call Legendre or something? So the theorem tells you that the number n factorial contains the prime factors p exactly this number. So what is it telling you? You take a prime p and you have an actual number n. Then this, the question is, what is the largest power? What is the largest power r such that p power r divides n? So the idea is p power r plus 1 does not divide n. I mean n factorial. So we have to find this largest power r. So that r is exactly this. Summation k greater than or equal to 1. This is greatest integer function. So this means the greatest integer less than x. And for any real number it is defined. It's a step function. We have been studying this in small classes, right? So what means if 2.5 greatest integer is what? Greatest integer less than x means the natural number, the integer which is less than this 2.5, that is 2. So that's the idea. So that is this function. So you have a prime p and you have nn. So what is the largest power of p which divides n factorial? So that power is given by this r equal to that. We can see some one of the example and some application, and then we move to the proof immediately. Then we will use it in our proof. So for example, we are going to calculate what is the largest power of 2, 5 and 10. So 10 is not a prime number, I will come to that, in 100 factorial. So let's calculate for 2 power 2. So the equation tells you that r is equal to k greater than or equal to 100 over 2 power k. So 100 over 2, 100 over 4, 100 over 8, likewise I am going, and 100 over 128 comes, 128 is greater than 100, so definitely it will be 0 point something, so that would be 0, like this. Other values we can calculate: 50, 25, greatest integer of 12.5 is 12, 6, 3.125 is 3. So when you calculate, you get a count which is 97. Similarly for 5, 100 over 5 raised to k, you will get 100 over 5, 100 over 25. This one, when you calculate, you get 24. So these are the largest power, or largest power of 2 divides 100 is 97, largest power of 100 factorial. Yeah, so largest power of 5 which divides 100 factorial is 24. Now you know that 10 is nothing but the product of 2 and 5, right? So even if 2 is 97 times are there, but that is not enough, because 5 is only 24 times. So right, so the minimum of that will give you a 10, right? Because you have to couple it 2 times 5, 5. So how many ways you can do this? Only the availability of 5. So availability of 5 is 24. Otherwise there is only 2. So that can be, so you can find this minimum of that 24. So this 10 we call a square free number. 10 is, that means square free means what? Square free. It is not divisible by a prime square. Not divisible by p square for any p. So that number should not be divisible by a square of any number. In fact, p we say. So this is, you can say this is so every prime has the power 1. That's the idea. So 10 is such a number, and for that you just want to find out the largest powers of 2 and 5 and take the minimum. Then you will get how many times 10 will divide that 100 factorial. So if you generalize this, if m is a square free number, and then n factorial, what is the largest power of this is easy, because we use all these numbers. Take all the primes. M is given by p1 times p2 times ps, and you find all the largest powers and take the minimum. You get the answer. I just mentioned it when. Now we'll go for the proof of this theorem. Proof is very easy. You can see this is just an observation. N factorial can be written as 1 times 2 times up to n. Right? That's the idea. So what I am going to do is I want to write n factorial like this. I want to fill these gaps. I mean, some gap. I mean, not filling the gap, but identifying the numbers in a different form. N factorial can be written starting from 1, 2, 3. Then I am going for p, up to p. Then again p plus 1, p plus 2 something. Then I will end up with the 2p. Then 3p, and how far I can go? I can go only the greatest integer of n by p, because if more than that will exceed n, right? Suppose you assume that p divides n. If p divides n, then n by p would be n by p itself. Now if you multiply it with p will cancel, you will get n. So any number which is greater than this one, greatest integer of n by p, then this list will exceed n. So that I don't want that. So I will stop up to here. Then definitely there will be a factor. Well, another factor. For example, I'll show you an example. For 5 factorial, you write 1 times a 5 factorial. Choose suppose p. You want p. P is equal to 2. So 1. Then 1, 2, 3 up to end up. I end up with the p. That is p. This is my p. Now I am going 3 to 3 something. Then I am writing 4. After 3 you have 4. That 4 is nothing but 2p, because 2 times, right, 2 times 2, 4. So I stopped here. Here I stopped. Now 5 is coming. So that is my m1. So after all this list, you get one more factor, which is 5 in this case, right? Yeah. Now you look at what is 2p here. 2p is exactly our final element here. For example, you can see 5 by 2 is 2.5. Greatest integer is 2. So 2 times 2 is 4. So in this case, this example, your final number n by p times p is 4 and m1 is 5. I just go through that. So in that way, what is the meaning? I am counting the p's, right? Power p, right? P, I got 1p, 2p, 3p. So how many p I get now? So I got n by p, greatest integer of that much p I got. But it is not enough. It's not enough, right? Why it is not enough? Because when I write 2 times p, this 2 is also that prime number. So I didn't count this. To count this, I do again in different fashion. Instead of going for p, I going up to p square. So p square would be 4, right? So that time I am counting that what is left here. Then 2p square. So how many times I can go? N by p square times I can go. So you get. So in this case, you are getting. So this many. I got this many primes in the first case. Now second case I get n by p square primes. Right? So now you have to add this both. Now I am not finished. Then I am going for n by p square p factors I got. Now I am going for p cube. doing the same thing, I got this. So in this case I got n by p cube p factors. These are all are new one, so all are distinct p factors, right? I am not counting, I am not double counting. In each of this case I am getting new one. So finally how much I get? I'll get up to the largest power of n, k, right? So how many that will be there? So that when I count, I get n p power k, right? P factors again. So when you add this all, you get this, because you are adding, like, first of all I got n by p, then I counted n by p square, then I got n by p cube, and finally I got n by p power k. Because if p power k is greater than n, then I cannot even start with that, so I finish. The another one would be 0. Pk is divides n, and pk plus 1 does not divide n. So this is the k here, right? So actually that k is determined here, maybe because that we don't know, and that we are going to describe that. So that is the r. And you stop somewhere now. That's the largest power of p. So for example, in this you can see, yeah. So this is the largest power of p, which divides n factorial, not n. This k, the maximum of this k is the largest power of p which divides n. This is n by s. That's a divide. So that's a proof. Here is idea. Okay. Yeah. Now we go to estimate 2n Cn. So what is 2n Cn? That is by example, n choose k formula. So n factorial by n minus r factorial times r factorial. So that would be 2n factorial divided by n factorial times n factorial, right? Now if you want to count suppose you take a prime number p, and if you want to find the largest power which divides this 2n Cn. So in that case you can see, you can find first the largest power of p which divides 2n factorial. That can be found by this, right? Then since n is less than 2n, so all the primes which divides n factorial should also will divide 2n factorial. So when you divide this number by this, all the primes which divides this fellow will be removed, will be cancelled out, and it is not only one time but 2 times it is removed. So what I am telling is the largest power of p, suppose you have you get something like p power some m. So that is the largest power. Now suppose the largest power of p which divides n factorial may be p power k, and you may have once again this happens. So this will be cancelled out, and finally what you are getting, p power m minus 2k, right? So only this much powers will divide this 2n Cn, right? That's the idea. So to get that, which is very easy, what you are going to do, you first calculate the largest power of p divides 2n factorial, then you remove largest power of p which divides n factorial 2 times, right? So minus this n power p power k minus this, then this will be, if you arrange 2n over p power k greatest integer minus 2 times of that. Now we will estimate this quantity, right? So in order to estimate that, you need to know one property of greatest integer function. Greatest integer function is always by the definition this number is an integer, right? This is greatest integer less than or equal to x. So in part of the definition itself, the box x is less than or equal to x. So that's not very difficult. Now we have to prove this one. 0 less than or equal to x minus mod x and not one box x which is less than 1, strictly less than 1. This is we have to just prove that. It's very easy. Anyway, so suppose we assume this is equal to 1. This is very clear, right? Because this is a bigger fellow, so if you take it out from this, of course it should be greater than or equal to 0, so that the left inequality is easy. To prove the right inequality, you assume the equality, and if you add that possibility, definitely it should be less than that, right? Yeah. Okay, so yeah, so look at this. Suppose x minus mod x, box s is equal to 1, right? So you must understand one more thing, that a mod box x can achieve so is it be greater than 1? If it is greater than 1, that means x greater than mod x plus 1, and that won't be happen. Okay, first we prove it is strictly less than 1, right? Yeah. So suppose it is equal to 1, then what happens is x can be written as 1 plus greatest integer of x. So this is an integer, this is also an integer, that means this is an integer. So if x is an integer, then greatest integer function gives you the same value. For every integer, if 5, you get 5 itself. So that means box x equal to x, and if you put it back, they both cancel out and you get 1 equal to 0. That is an absurd idea, right? So surely x minus mod x cannot be equal to 1. That case we have ruled out, right? Now a question is there, that is it greater than 1? This quantity is greater than 1. So if it is greater than 1, then we have x is okay, we'll talk about that. X minus 1 is greater than mod x, right? So that means mod x less than x minus 1, which is less than of course x, right? Right. So this won't be happen. You can think of that, right? So this can also, we can rule out, and you can talk about any number if you want to. For example, I can give you 7 minus 7.5 minus greatest integer of 7.5. So this is, you will get 7.5 minus 7, this is 0.5. So this is not greater than 1. So I can give you an example for time being. So you find out a convincing proof. It's your task for you, right? So so this won't happen. X minus mod x cannot be greater than 1 for any real number, right? And even though it is less than, now we are avoiding that thing, then it is not equal to 1 also. So we will get this inequality, x minus mod x. So from that we can prove that x minus 1 is less than box x, right? So x minus 1 is less than box x. So using this we can estimate some idea, right? So you can see that 2n by p raised to k, so if you take this as an x, then by normal idea gets integer of x less than or equal to x, you can easily infer this. Now as we now proved this one, x minus 1 less than box x, you can apply this for n by p power k. So n by p power k minus 1 is less than n by p power k greatest integer. Floor function, this is called, either you can use this or you can use this, both are same. Both in this is called, we call floor function also, greatest integer, also called for GIF. They both are same. Okay. So from this I multiply by minus 2, so the inequality will reverse. Now I can estimate this. Instead of this one I can apply this, right? So when I apply this, you get 2. So that means this quantity, this summand, right, that we have started with, this summand is less than 2, that means it's at most 1. So summand is less than or equal to 1. So the summand is equal to 1, that means, and also we know that when p raised to k is greater than 2 times n, definitely that summand is vanishes, right? The summand will vanish. So then we can exactly we can say that this number is at most 1. So if I replace this with 1, what I get is summation k greater than or equal to 1 here, right? And how far it can go? It can go the largest power of r, which divides 2n, or I can say the power p power r which is less than or equal to 2n. So largest power of r which divides 2n, or largest power of r which is less than or equal to 2n, right? That's the maximal way I can go for this, and after that it will be 0. So what is this telling? So this is 2n cn, right? This is the largest power of p which divides 2n cn. So that means largest power of p that divides 2n cn is not larger than 2n, right? So we can see that this is this quantity is a maximum of r such that p power r less than or equal to 2n. That means the largest power of r, right, less than 2n. So the prime which the largest power of p that divides 2n choose n is not larger than 2n. So that's a very important thing. Now in particular, the primes greater than root 2n will appear at most once, because if it appears at least 2, then p square will be greater than 2n. That's not possible because it's a factor of 2n, right? So that is the idea. Okay. Yeah. So now let's prove the remaining part in the next part. So next we'll prove that the primes p that satisfy this inequality, that means in between the primes between 2 by 3 n and n, they will not divide 2n choose n. So that's our next proof. Okay. So you think of an argument why x minus mod x cannot be greater than 1. While I was doing this, I haven't think about it, right? So you can rule out this case by some kind of contradiction, right? So otherwise in the next part I will be doing that. So at least we have avoided the equality, right? And we have also ruled out this thing with an example. Then we showed that this is less than 1. Okay, but we can go for a mathematical or rigorous proof also. Not very difficult. Time being, I am missing that. Okay, so in the next part we will prove the fact that in between 2 by 3 n and n, there is no prime factor for 2n chosen. Thank you.